Thank you, Sharon, and good afternoon, everyone, and thank you for joining us today. My name is Rich Skradsky, and I am the Northeast Regional Manager for Teledyne ISCO. Before I turn over today's webinar to Darrell Kuta, one of our flow meter business development managers, I'd like to take a minute to introduce you to our company. Teledyne ISCO was originally founded in 1958 in Lincoln, Nebraska, where it has remained until this day. Our environmental division was created in 1969, specializing in the manufacture of rugged instruments used by environmental professionals in the water, stormwater, and wastewater markets. We have been protecting water quality all over the planet for the last 50 years, having invented the world's first automatic wastewater sampler in 1971. We are a true manufacturer, not just an assembly house. So when we say we are made in America, we mean it. Today, Darrell will be sharing with you some fundamentals of open channel flow measurement, knowledge that he has gained over the past 26 years while working at Teledyne ISCO, and knowledge gained by ISCO over the past 50 years in the industry. After all, we wrote the book on open channel flow measurement, first published in 1978 and updated through 8 editions. If you would like a copy of the handbook, you can request one from our website at teledyneisco.com. We thank you for your business and stand firmly behind our pledge to continue to build great products and provide quality service and support to all of our customers for many years to come. With that said, I'll now hand things off to Darrell. I hope you enjoyed today's presentation.
And thank you for joining me today. I am Darrell Kuta, Business Development Manager for Water Products, and I'm here today to talk to you about the fundamentals of flow meter technology. So what is needed to measure open channel flow? Well, you could use a primary device, which could be a Weir or a Flume. You also need a secondary device, which is considered a flow meter or a flow logger. I'll talk more in detail about that later. And last, you need a sensor. That could be either just a level sensor in combination with the Weirs and Flumes, or you could use both level and velocity to calculate flow in applications where you don't have a primary device. Let's first take a look at primary devices. What is a Weir? So a Weir is a dam that's built across the channel, and it measures the flow based on the water level going over the top of the Weir. And so then that will provide a flow rate that's proportional to level. Now, Weirs come in a variety of shapes. They can be rectangular, with or without end contractions, a V-notch Weir, trapezoidal. As you can see, there's lots of different options for Weir shapes. Now, one of the important things to know about a Weir is the actual sensor placement. And I'll talk later about what type of sensors are available for this, but the key thing is you want to avoid the drawdown. So what that means is that you need to get the sensor mounted far enough upstream to get a representative level of the water going over the top of the Weir to avoid the drawdown. But a couple things you need to consider. What is the expected flow rate? And that is going to determine the crest height, where you place the sensor, and other factors for a Weir. So as far as the measurement location, it should be 2 to 3 times the maximum height. So when you look at what the expected flow rate is, you can then back check with the ISCO Flow Data Handbook to determine what the maximum level would be. The height of the Weir is also going to be dependent on the expected flow rate. So if you expected a flow rate of 5,000 gallons per minute, and the maximum water height is 1 foot that would go over the Weir, you'd need to make sure that Weir wall is 2 to 3 feet high. And remember, the flow rate is calculated from level above the Weir. So we're only concerned about what's going over the top of the Weir to calculate our flow rates. So where are the Weirs used? Commonly used at the effluent wastewater treatment plants, the industrial discharges and streams as shown in this picture here on the right. So what are some advantages of the Weirs? The nice thing about it is that they can be low cost. They can be made out of metal, wood, or steel. They're easy to design. In fact, I've been to job sites where they've just taken a piece of plywood and cut a V-notch out of it. So it was cheap and easy to design, and sometimes they're easy to install, depending on your application and how large the weir is. But there are some disadvantages to a weir. You do have the high head loss because you actually have an obstruction going across your flow stream, which then could lead to periodic cleaning. So if you have a weir or dam across your flow stream and it's a natural channel, you have to worry about branches, trash, other things that could collect on the front of the weir, which then would require going out and cleaning that every once in a while. Now, another primary device is a flume. So a flume also provides flow rate proportional to level. It does slightly restrict the flow going through there, but the idea of a flume is that it restricts the flow a little bit, which causes it to accelerate the velocity through the flow to the throat of the flume, which essentially makes them self-cleaning by flushing the debris and accelerating the water through the flume. So there's three different parts to it. The converging section is where you're going to take your level reading. The throat size on this example of a partial flume determines the size of the flume. So if you can go out there, measure across it at the narrowest point, that will tell you what size your flume is. And last is the diverging section. This is where the water would free flow out of your flume. So when you go out and look at a application, the converging section, the approach, the level should always be higher than the diverging section. If you find that they are equal, you know you're in a surcharged condition and thus getting incorrect flow readings. So you always want to make sure you have a free flow condition. Now, where are flumes used? They're commonly used at the influent of wastewater treatment plants, stormwater discharge, industrial discharge. And what's in common with all these is that there's potential for debris that could go through there. And that's why they use a flume, because it's self-cleaning, whereas a weir would require some more maintenance than a flume. So with all primary devices, weirs, flumes, they all need a level sensor. And I'm going to talk to you about the common level sensors that are used with both. And what they do is they read the level and they calculate the flow based off of the channel shape or primary device that you have put in there. You can also go out and just take a manual depth reading with a ruler and then look at the flow data handbook to determine what your flow rates are. So as far as with weirs and flumes, you always want a good free-flowing application because the flume and weir are unable to detect the direction of flow because they are a level-only device and just level to flow calculation. Now this picture here is showing that I mentioned that flumes are mostly maintenance-free because they're self-cleaning, but that's not always true. So in this example, it's showing that there's debris that's obstructing this flume. So there is some maintenance required where you have to go and actually clean out the flume periodically. And so what could happen here with the debris, it actually backs up the flow. But what would you expect to see out of your flow rate in this application? Well, as we can see, there's a lot more water upstream than there is downstream. So because it cannot detect the velocity of the water, it just goes on level only. In this case, it would actually overcalculate your flow rate. Whereas you can see in the bottom of that picture, we just have a smaller amount of flow coming out. So you'd have inaccurate flow readings. Now we do have some options for recording your flow. And what your options are is you need to consider, do you have AC power or DC power out there, or even solar panels? So depending on your application is going to determine how you want to actually store your data. So your choices are, you can have a permanent meter or a portable meter. But first, let's talk about the portable data loggers. And what's different about them? Well, portable, as it says, you can move it around from site to site. They're usually battery powered. They will commonly have an option for AC power if it's available. They are IP68 rated. What that means is that they can handle temporary submersion and still continue to operate. which makes it ideal for manhole applications where you can hang it off of a manhole rung or something, because the environment in that sewer is going to have high humidity and moisture. And so having an IP68 rated logger will keep it watertight, airtight, and maintain its integrity. Now, the biggest difference between a flow meter and a logger is a logger does just that. What it does, it will wake up, take a reading, and then shut down. And it when you take those readings every 5 to 15 minutes, it takes the reading, assumes that the flow rate and levels are going to remain consistent during that off period, and then it wakes up again, takes another snapshot. And it'll give you a pretty good representation of what your flow rates are. And a lot of these loggers will have the option to add a modem. Now let's take a look at the permanent meters. So the difference is a permanent meter, it takes continuous readings. So it's updating readings like every 10 to 15 seconds, whereas a logger was updating every 5 to 15 minutes. So with that, it's going to require more power. And that's where you'd want to have AC power available, or possibly DC power with solar panel. The biggest thing with the permanent meters is the flexibility. As shown here with the ISCO signature base meter, you can add different types of sensors to it. You can interface it with a water sampler. You can have different ways to access the data. You can add cell phone modems to it, alarms, so you can trigger off of any parameter you're monitoring: pH, temperature, flow, level. So if you hit some type of a high alarm condition, you can have a modem on these devices to automatically let you know when you've hit that alarm condition. You have the ability to download the data with a USB flash drive, or go out there with the Flowlink software, connect to it, download the data. And then other outputs available are SCADA to your SCADA system using Modbus or analog output. So you have a lot of flexibility with the permanent meters. So you just have to analyze your site and determine what's best for you if you need a logger or more of a permanent meter. Now, which sensor should you use? I'm going to talk to you about the different sensor types that we can use with the Weirs and Flumes, where they're used, advantages, disadvantages. And first, let's take a look at the common non-contact level sensors. That's going to be your ultrasonic sensor and the radar sensor. And then more the in-water sensors would be your bubbler or submerged probe. But first, let's talk about how the radar and ultrasonic sensors operate. They transmit a sound wave. It bounces off the surface or the floor, detects the echo, and what that is a function of time. It determines how long it takes to get that return signal to, it will calculate what the distance is, which would in turn be able to calculate what your water level is. Now, all ultrasonic sensors have a deadband because it takes a certain amount of time for that transmitter to send out the signal, turn around, and wait for that return signal. And so that deadband actually amounts for the amount of time it takes to transmit and receive that signal. So depending on your manufacturer of the ultrasonic sensor, you may have to mount it, 1 foot, 2 feet above your maximum water level. Now, what are some of the advantages? They're non-contacting, so it's going to make them more maintenance free because you don't have to worry about debris or other things getting caught on the sensor. They're easier to install because you do not have to stop the flow to install your sensor. As I mentioned, they're maintenance free because they're out of your flow stream. But there are some disadvantages. You may be restricted on space, so you do have the deadband. The beam angle, if it's too narrow of a channel, the beams could actually bounce off the sidewalls and give you a false echo. And they can also be affected by wind or steam or foam. So the wind can actually essentially blow away your signal to get you a weaker return signal. Steam and foam will absorb that ultrasonic signal to keep it from giving you a strong return reading. And surface turbulence. It needs to be able to bounce directly back into the sensor. If you have really turbulent water, that signal is going to bounce all over and either get a weak or no return signal at all. Now, the radar sensor, the advantages are it's also non-contacting, which makes it maintenance free. One of the biggest things is the distance. An ultrasonic sensor range is usually 10 to 30 feet, depending on which one you buy. But radar sensors, I've seen them where they can mount them like 100 feet away, which makes them fantastic to put on bridges or large tanks. Uh, so it does give you a lot of flexibility on greater ranges. And another big thing is that a radar sensor can actually read through the foam and steam. It can actually tell the difference between foam and steam and when it actually hits the surface to get you a valid level reading. Disadvantages, they're usually a little bit larger than the ultrasonic sensors, and they also have trouble reading a turbulent surface. And the cost of a radar is usually a little bit greater than what you'd find on an ultrasonic sensor. Other types of sensors are the bubbler, one of my personal favorites. And what that does is with a bubbler meter, they will have an air pump built inside. They build up air pressure in an air tank. And then the air is slowly released through a control valve. And then as it goes through the transducer will then read the amount of pressure it takes to push one bubble out, and that will relate to the actual level. So the advantages, they're suitable for small channels because you just have an 1/8 of an inch bubble line in your channel, so you don't have to worry about it hitting the sidewalls or anything. So you can put it in very small applications. It isn't affected by the wind or steam or foam or lightning, any of those things, or even temperature, because it's you just have a vinyl bubble line. There's no electronics in the water, so it isn't affected by any of those things. And only the bubble tube contacts the flow. So the nice thing is that if it is a corrosive environment and something happens to that bubble line, you take it out, replace it. It's usually pretty inexpensive to replace a bubble line, and they're just as accurate, if not more accurate, than an ultrasonic sensor. Now, some of the disadvantages: it is a bubble line, so it could get restricted if there's a high sediment. So you may have to take into consideration where you're going to place that bubble line to keep it out of the debris. And because it has a air pump in there, it may have a little bit higher power consumption than an ultrasonic sensor. Now, other types of sensors are the differential pressure transducer. So they reference atmospheric pressure. As you can see on this probe, there's little holes on the side of it. And so the water seeps through there. It measures the amount of head pressure over the top of that sensor. Now, the advantage is you can also put it in small channels. They're not affected by the wind, steam, or surface turbulence because it's below the surface of the water. And one of the biggest advantages of this is that if the sensor does get covered with silt or debris, it still can sense the head pressure over the top of it. Now, keep in mind, it isn't reading velocity, it's just reading the pressure over that sensor. And so it can still give you an accurate level reading. Now, the disadvantage is that chemicals in your flow stream, because you do have electronics in that flow stream, depending on what it is, it could actually break down the plastic in the pressure sensor and then damage your sensor. Debris could tear it out. High temperatures have been known to affect pressure transducers. And because we do have an electronic device in the water, lightning could damage it. So what do you do if you need to calculate flow and you don't have a primary device? All you have is the level sensors I was talking about. Well, one, you could use a lookup table. So you could work with the hydrologist to come up with a level to flow table. Depending on the channel, you may be able to find up a lookup table like this. So you just find the level and then the associated flow rate with it. Again, it won't tell you the direction of it, but it'll look at the level and give you a flow calculation based off the level. Other things you can do is use a Manning's formula. Manning's has been around for a long time. And nice thing about Manning's, if you can calculate the slope of your pipe or channel, and then if you know the roughness, the ISCO Flow Data Handbook has a nice table showing the different options, what the estimated roughness would be for a concrete pipe or a natural channel. So it gives you an idea where to start. You know, Manning's, it will tell you that you have more or less flow based on level, but it's highly susceptible to the accuracy based on what you put in there for the slope and the roughness. And the roughness, that can be kind of a moving target, as shown in these pictures. If we have a natural stream or it starts out as a clean concrete channel and we start having vegetation grow in there, well, now my roughness changes, which is going to affect your flow readings. Now, common applications where you're going to be asked to read flow without a primary device are going to be a round pipe or possibly a rectangular channel. And to do that without using the Manning's formula, what we need to know is the geometry of the channel or pipe. We need to be able to calculate the water depth to give us the wetted cross-sectional area. And then we need to know what the average flow rate is. And so with the level and velocity, we're able to get our flow rate. Q equals area times velocity to get our flow rates. And a couple of common velocity sensors would be your continuous wave Doppler sensor. And the way that operates, it has a pressure transducer I talked about before to read the water depth over the sensor to calculate the wetted cross-sectional area. They transmit a frequency into your flow stream, and then it determines the velocity by the frequency shift, and it will also tell you the direction of the flow based off that frequency shift. And it bounces off of air bubbles in the water or particles to get that return signal. Other types of velocity sensors are the magnetic point velocity sensor. This probe, you set that in the flow stream. Sometimes there's sensors that actually mount on the bottom, and it produces a magnetic field about the size of a softball. And as the water breaks that magnetic field, it induces a voltage that is proportional to velocity, so you can tell which direction and the speed of the water. Other velocity sensors you may run across would be the propeller meter, as shown here. Pretty simple design. It just calculates the velocity based off the RPMs of the propeller. And if it's going reverse, it can also calculate the reverse flow. So what are the advantages of an area velocity sensor? Well, no Weir or Flume is required. No need to estimate the slope or the roughness of your channel. And it's a lower cost than a Weir or a Flume. Because you don't have to put in all the design work to put in a flume. Flumes can be quite expensive if you have to put in do a lot of excavating, concrete work, and there's a lot of things that could go into that. One of the biggest advantages of the area velocity sensors is that they can work in open channels or full pipe. It'll tell you when it's in a surcharge and even if you're having reverse flow. So those are big advantages over the primary devices, the Weirs and Flumes. But with everything, there are some disadvantages, and that would be the debris or silting over the sensor. They'll still read the level, but they may not be able to read velocity. And with any flow metering application, turbulence and swirling will affect your flow readings. So you always want to make sure you have an application that has good, straight, and uniform hydraulics. So what are my other options? Well, your other common types of velocity sensors are the non-contact, which are laser, radar, and ultrasonic. So why use a non-contact AV sensor? Safety is one of your biggest concerns, and maintenance. So they kind of go hand in hand. If you have to do maintenance on the site because you have debris covering the sensor, you're going to have to send somebody down there to clean it off. And then that's going to cost you more money. Every time you go down down in the hole, it's there's always a danger to send anybody into a hazardous area. So what are some of the common non-contact area velocity sensors? Well, we have the laser subsurface velocity sensor, the radar surface velocity, and the ultrasonic surface velocity sensors. And I'll explain how each one of those work. So with the principle of operation for the laser flow sensor, it uses an ultrasonic sensor to read the distance to the surface of the water. Once it knows that distance, then it can fire the laser below the surface of the water. The key is it's trying to read the peak velocity below the surface of the water to then calculate the average velocity. And while this laser's on, it's on for about 2 seconds, and it takes 5,000 spectral readings to get the velocity reading. So it could take anywhere up from 5,000 up to 75,000 velocity readings to come up with one velocity average. Now, the frequency shift, as shown before, determines the direction and the speed of the flow. And and this is essentially what it looks like. The laser goes through a lens, which then focuses below the surface of the water. That reflected energy is directed back into the laser diode, and then the frequency shift is going to determine the direction and the velocity of the water. Now here's what that data looks like. When that laser's on for 2 seconds, internally, this is data that you can collect from our instruments, and it shows you the return spectral signal. And as more of those readings agree with each other, you're going to see a higher peak and a narrower peak. So that indicates that you're getting a good, strong reading back. So diagnostics are important to determine that you're getting a good, reliable reading. And so with this high signal to noise ratio, it allows us to actually read extremely slow velocities, which have just been unheard of in the area velocity flow market. We're able to accurately read down to a quarter foot per second. Now, what that looks like is we have the option to do a multi-point, multi-depth velocity method. So we take a level reading, and now we can transmit the laser up to 15 points below the surface of the water. And with all these points, it's user defined. You can choose up to 15 different points, depending on your application. Now with the non-contact sensors, with the radar and the laser, they both have similar mounts, how to secure them. They'll have 2 anchor bolts to bolt it to the wall. You have an adjustable bracket that allows you to adjust the pitch and the roll. You can move it up and down. Now the laser flow allows you to point upstream or downstream to get your velocity readings. And minimal experience is needed to install it. Field crews are fantastic with putting anchor bolts in the walls and securing equipment. But if you do need assistance with that, you can always contact ISCO product support or your local representative to help you through your application. Now, maintenance. With the non-contact sensors, with the radar and the laser sensors, they offer extraction tools so you can remove it from street side, as shown here on the picture on the right. So it makes it easy to remove. Once it's installed, you grab onto the top of the sensor, turn the handle, lift it out. And so this is going to help reduce your confined space entry. It increases your safety. And as you can see, the fewer times you have to send somebody down into the sewer, it's going to save you a lot of money on confined space entry, and the job's going to be a lot faster to be able to easily extract your sensor if maintenance is required. Now the radar sensors, so they mount above your flow stream as well. And what it does is uses the radar to read the surface velocity. And then it averages the velocity based off its return signal. Now, keep in mind that with any surface sensor, it needs ripples on the surface of the water to be able to get that return signal back. If you have a slow velocity, like say less than 0.8 foot per second, the surface becomes smooth, and then that signal can actually bounce away from the sensor and not get a return signal. So then you would go into error. Similar problems would happen with the outdoor applications. If you have a lot of wind, that could actually end up blowing your signal, the surface water different directions and giving you a false velocity reading, whereas reading below the surface will allow you to get a true velocity reading. Now, ultrasonic sensors, they operate the same way, but what's different about them is that instead of mounting it in the chimney of the pipe, you mount it inside of the pipe. So you lose the ability to use that extraction tool. However, it is still non-contact, but it uses the ultrasonic level and velocity, and it will need the ripples of the surface to be able to get a velocity reading. Now, where are they used? You can use them in small channels which I consider anything less than 3 feet is a small channel. You can use them in large channels as well. So the key is that you need uniform flow going through there with the large channel, or you may need to put multiple sensors across that channel to get good velocity readings or good average. So where are the non-contact sensors used? You can use them in stormwater applications, which they're ideal for stormwater because you don't know what kind of debris is going to go through there, shopping carts, trees, anything. So, that would actually potentially tear out an in-pipe sensor. So having it above the flow stream is going to save you time and money, unless you're able to mount them on natural channels also, rivers and streams. So some of the physical characteristics of any area velocity application is that you need uniform flow is critical to getting accurate data. Um, so depending on how fast your velocity is going to determine how much straight run you need in front of the sensor, or if you have any adjoining pipes, that's going to create swirling. So you want to just make sure you have a clean straight run in front of your sensor, but in front and behind, to give you accurate flow readings with any area velocity meter. So what are the advantages? No Weir or Flume required. Safety. So if we can stay out of the flow stream, it's going to be much safer. It's going to reduce your maintenance by being non-contact. The installations can be much easier because you don't have to stop the flow of water going through there, and you can mount it above your flow stream. And the other big thing is that it can read both forward and reverse flow. Some of the disadvantages, if you do have swirling, non-uniform flow, um, bad flow characteristics, going to give you bad data. And then other disadvantages would be if you have thick foam or steam on the surface of the water that could affect the ultrasonic level reading. That would be a disadvantage. So now that you've seen different applications, the different types of sensors, and you've decided what type of logger you need for your application, you need to ask yourself, how are you going to retrieve the data? Are you going to be able to go out there and directly download? Do you plan on installing a modem so you can either push the data or call it up and pull the data? So these are all important things that you need to determine at the beginning when you're deciding what technology you're going to use. And also you have the option to do continuous outputs, either Modbus or analog output. So you need to take all these into consideration when you're setting up your application. Now, one thing that we offer is a cloud-based software called Flowlink Cipher. The Flowlink Cipher has a dashboard view and a map view, so this allows the user to quickly just glance at your data and easily see, how smoothly everything is running. With the quick data analysis, you can custom build your graphs or tables that you want to see, and when you open it, you can easily determine if maintenance needs to be done on site. One of the biggest reasons people are starting to go to cloud-based software is to reduce the hacking risk. If you don't have a server on your premises, you don't have to worry about malware and other wares that can potentially damage your data. This data is stored on Amazon web server. It's got triple redundancy protection, so your data is always going to be available to you. And the other big thing is data anytime, anywhere. Big storm events don't always happen between 9 and 5. So when you're sitting at home, you can pull out your cell phone, take a look at the data to have an idea what's coming up for your job next week. And automatic updates, that's a key feature. In the past, with the software that you'd put on your machines, if there were updates, you had to uninstall it, install new patches. But when it's in the cloud, all that can be done in the background and automatically update your data. So if you have enhancements, it's all going to be done right away. Some things that you may want to look for in your data is you want to make sure, or your software, you want to make sure that it's easy and intuitive. As shown here, we have a dashboard that you could customize if you prefer to see your data as line graphs, scatter plots. I've had people where they've had graphs created of just voltage only, so they could easily take a look at their sites, look at all the voltage to determine if they have to go out and do maintenance on one of their applications. Other things you want to look for in a software program, just to make your life easier, is you may want to add mapping. So GIS mapping. So you get a quick overview of all your sites all at one time. With the Cipher, we have pinpoints that will actually change color, so you can see all your locations. If they're, green is good, red indicates you've hit an alarm condition, maybe it's a low battery or it's a surcharge condition. So then it helps you to plan on how you want to deploy your technicians for the day, and all at just a quick glance so you can see all your sites. Other things you may want to consider is a software that has the ability to add attachments. So as shown here, if you're able to install a graph or a image of your site, work orders, that way all your crew members are all on the same page. They can go here, see what the site looks like, see what they need. You can even put notes in there as far as, to bring a shovel, because this site is known to have a lot of sediment. Other things you want to look for is the ability to put additional data on your site, be able to put comments on there. As shown here, we can show that it's an active site, it's actively pushing data, what the voltage is for each site. But the key takeaway to all this is you want to know which flow meter technology should I use. The answer is there is no one technology that should be used for all application. Your decision is going to depend on the following. If you already have a Weir or Flume there, can you put a primary device in? Is it cost effective to put in a primary device? Or if you have an existing one, it may have been maybe fallen apart or undersized, so you may need to decide to remove it, put a different primary device in, or go with one of the area velocity type sensors. If you have an open channel, you've seen the different options for in-pipe sensors, or if you only have a level only device, you can use the Manning's formula or data tables. Non-contact sensors are becoming one of the more popular sensors, just because of the maintenance, reduced maintenance, the easy to install. And then you also want to consider the accessibility. How are you going to get your data? You need to take all these things into account. Are you going to be able to get out there to easily extract the data, or do you want it to automatically push, send you automatic notifications that there's a problem? And then you also want to look at the maintenance. The type of sensor you're going to use is going to depend on maintenance that's required. If you've already have an AV sensor at your application and you find you're going out there once a month to clean it, maybe it's time to start switching to a non-contact sensor instead. So with that, I thank you for your time today. Again, my name is Darrell Kuta. I'm at Teledyne ISCO. As you can see on my screen, my email address is darrell.kuta@teledyne.com. Feel free to contact me with any questions you may have, and have a good day.
Well, thank you, Darrell and Rich, for sharing your expertise. And we would like to open up this section for any questions. Please submit your questions through the Q&A function. We currently have Darrell and Rich, plus Rick Dye has joined us. So don't consider any of your questions too big or too small. Please input them, and these gentlemen would be happy to answer. Darrell, it looks like we've got our first question. Would you like to take that?
Great, thanks, Sharon. I'd be happy to take that question. The first question that's come in is there a limitation on how high above a channel a non-contact sensor can be mounted, i.e. Mounted over a river, mounted under a 100-foot bridge? So as far as that type of measurement would require a radar level sensor, And so it wouldn't be able to read the velocity, but you can read the level from that type of distance. So yeah, I have seen the radar level sensors. They work fantastic for that type of applications, just because of the distance and the temperature gradients from that far distance. The radar would work better than an ultrasonic sensor. But it would be a level only. And then if you needed flow calculations, then you'd have to develop some type of a flow table based off of the level and area.
Right.
And Rick,
Yeah, I got another question here. Let's go ahead and go with that. Are there any devices you would recommend for measuring periods of no flow? In the case of a no flow scenario, you're probably better off using, like, for example, the laser flow would be a good one. Uses ultrasonic for levels, so that's not going to drift. And the laser itself isn't going to drift. So you have nothing in the flow. That's probably your best method. The one thing to keep in mind, though, is if that sensor is in the sun, you would want a sunshade, and that is only for the level part of it. So typically area velocity sensors that are in pipe ones, they have a kind of a temperature issue when you're sitting out there and no flow. They can heat up, and then you get a rain event and you could have some significant level drift.
all right, thanks, Rick. Next question is, how does ice affect sensor selection? That's a great and timely question for this time of year. Because as far as like an in-pipe sensor, an AV sensor, you could put that in a flow stream, where there would be ice on the surface, but still moving water down below, where the sensor's at is fine. But if you have an AV sensor or a pressure transducer that freezes solid, that can actually deform or damage your pressure transducer or the sensor. So you wouldn't necessarily want to use an AV sensor or pressure transducer in ice. Now, a bubbler, as far as you could put that in there, the nice thing about that is that if it did freeze and constricted, it's only the bubble line that would potentially get damaged, and you wouldn't get accurate readings during that time. But it's going to be the most cost-effective option. So ice is a little bit tricky, because even with ultrasonic sensors, you get ice on the surface, that's all you're going to read is just the ice. You wouldn't be able to see the actual flowing water. Rick, did you have any more to comment on the ice?
Not really.
Okay.
No, I think you nailed that fine. We've done a lot of testing. We did a presentation on what we called a polar vortex flume application, which was up in Minnesota. And we had a laser out there because their flume would freeze up. They would have big chunks of ice on the side, which would make their flume not accurate. So they put a laser in front of that, and it did really well for them. Okay, I have one here. Laser flow looks great. Hydraulics are rarely as clean as you show in your photos. There are plans to downsize so you can fit like the ultrasonic showed. And we do get that comment sometimes. Oh, the laser looks a little bit larger. And what the main reason it is because it does the side-to-side scan, the multi-point scan. And we just need the room to be able to mechanically move the laser where we need it in order to do that. Keep in mind, though, that the laser doesn't need a lot of room to get a reading. So we'll have a lot of cases where people will cut a 4-inch wide by maybe 12-inch long slot in the top of a pipe, and the laser's mounted on that, and it's able to scan and do what it needs to do. And once that thing is installed, you're really not going in and doing a whole lot. So the size is becoming less and less of a factor.
All right. Yep. The next question is, do sewer gases have significant effect on ultrasonic accuracy? From what I've seen, the answer is no. I guess it depends on, if the gases have a large create a change in temperature, but ultrasonic sensors have built-in temperature sensors to compensate for the speed of sound. If it was outgassing enough that it actually created a fog, then it could possibly have problems. But, as far as sensors, they're designed to go in those sewer applications. So like just standard H2S gas, I have not found that to be an issue with the ultrasonic sensors. They're built with the right plastic and glue and everything to withstand that type of an application.
Yeah, and we've seen a lot in applications. Phoenix is a great example, a lot of hydrogen sulfide gas, and we have not seen a problem with the accuracy of the ultrasonic. Here's one. Is it possible for a bubbler tube to partially clog up, but not to the extent where the airflow doesn't come out at 1 bubble per second, but enough to cause an error in the recorded head measurement? And it's interesting when you partially plug a bubble line that's supposed to be putting out 1 bubble per second, it tends to put out more than that, but they seem to be smaller bubbles. Yes, that will affect, though, the overall level measurement. So with all of our bubbler devices, we have a lot of purge capabilities. The Signature now puts 15 PSI pressure through that line. So when it does a purge, it really does a great job blowing that out. So we are on, I believe it's our 6th version of bubbler technology, and we've made a lot of changes, enhancements, improvements over time. So we don't see a lot of that. But yeah, if you have a plug line or partially plug line, that's not a good thing. So you want to minimize that as best you can.
The next question is, what are typical issues that tend to arise with these applications, and how are they overcome? And I think you're referring to the bubbler still. As Rick mentioned with the auto purge, so the ISCO signature meter will output 20 PSI. So if it starts to sense that there's a blockage in that line, it'll send a large burst of air out to clean that out. If it can't overcome it, the meter will essentially protect itself and stop trying to purge into a deadhead, if that's the case. But what you can do to avoid problems with clogging the line is the bubble line doesn't have to be mounted at the very bottom of your channel. You can have it raise it up off the bottom so you're out of that silt level. You still calibrate your level to the actual level, and then it'll keep track of it from that point. So yeah, it doesn't have to be on the very bottom. So that's what I'd recommend. Either raise it, use the stainless steel bubble line to keep it from clogging, and then periodic cleaning, you may have to actually just remount that bubble line to get any lodged sediment out of it.
Going on that, I'm just going to make a quick comment. One of the biggest questions we get would be like level sensor drift, whether it's a pressure sensor only or one used with an area velocity. And honestly, the biggest problem is reference to atmospheric pressure, which is typically related to the desiccant. So as long as the desiccant is maintained, you should have very little chance of drift on a pressure sensor. One thing we do as well with the Signature is we will record that humidity level as well, so you can alarm off that. So now you know when you need to go out and do some maintenance on that. Okay, I'm going to go ahead and take the next one. We have a channel that acts like a sewer for a paper machine. A lot of fiber in the sewer. How accurate would a laser flow be if it cannot penetrate very far, or can it? The question, or the answer really is, it is going to see what it will see, and it's going to base that penetration on depth of water. So if it is really, really thick and you have floating paper on the top, worst case, it would see what's moving on the surface. You may have to do some adjustments on your velocity coefficient if that were the case, and it may not be able to see through it. But with the diagnostics that we have with the laser, we will know immediately how far it's seeing, what it's seeing, and is it going to work in that application. So, but when you're working with something like that, you don't have a lot of choices. Fiber, flumes, that's not a good thing. Area velocity in the bottom of a channel, not a good thing. So really any non-contact would be your best approach on that.
All right. Next question is, do non-contact laser flow sensors have any way of reading if flow surcharges and rises over the mounted position of the unit? That's a great question. And yeah, what we can do for that is we have a surcharge sensor. It's the area velocity sensor, and it mounts on the bottom of the laser flow sensor. And so as the water comes up and starts to submerge the laser flow sensor, it will automatically switch technologies to the pressure transducer and the continuous wave Doppler sensor to continue to read both level and velocity and calculate flow during your surcharge. So it can read both positive and reverse flows.
Okay, I'm working for a brewery that is looking to connect municipal sewer to a 4-inch pipe. They want to measure that flow, which will be irregular and in batches. What would you recommend? We have used the laser in pipes like that, where you have a very small opening. You don't have a lot of choices, unfortunately, with what you're looking at doing because of such a small line there, and you won't have full pipe. So a mag meter makes it very difficult to do that. But we have, again, you need a opening large enough to get the laser beam through, and you can do a laser with a 4-inch. The beauty of the laser, and where we're seeing a lot of applications now, would be industrial monitoring, where they may have a 6-inch pipe. And a lot of times there's very low flow, if no flow. And then when they have an event or they're cleaning tanks or whatever they do, batch dump, then we're able to read both the low end and the high end of that. So something like with what you're trying to do on a 4-inch, I would say send Darrell some pictures. You could send them to me as well. And we would take a look at it and go, okay, this is what I would do. But you have a challenge on those kind of applications because you put a flume in, it may not be rated for that low flow. And once you get the batch dump, then you have a problem there as well. So, but that's the first shot would probably be the laser.
Yeah, thanks, Rick. And yeah, and if it's a difficult application like that, a 10-second video that helps a lot as well. Is site pictures. And all right, so the next question came in is how important is it for a bubble tube to be placed in the center of a channel? We use a 730 flow module with the 6712 auto sampler. So as far as level is going to it's going to find its level across your channel. So you really don't have to mount the bubble tube in the center of the channel, because it's, if you have it on the, if it's a rectangular channel or a round channel, you could mount it on the side and still calibrate your level, and it's going to read the depth over it. In fact, on flumes, you'll notice that where the bubble line is placed is always on the very edge of the flume, or sometimes it's even in a stilling well. So that's outside of the flume, because the water is going to equalize across the whole channel. So yeah, you can place it in the center or to the side.
Okay, what is the recommended for very low stream depth, less than 1 inch? Good question. Pretty much everybody, I think, area velocity system will read down to 1 inch. What we do is we do a lookup table or a rating table. Once we get above 1 inch, we turn on our velocity, we start getting readings. It goes below it, and then we can either go to 0, or we can use the last good reading that it had, or use the rating table. But going up to 1 inch is kind of a algorithm thing, and it's just going from 0 to 1 foot per second when you first install it. So once you get above 1 inch, a normal AV sensor that's on a ring, contact sensor, will do a good job when it goes below it. But if you want to measure, we see a lot of what's called personal property I&I studies now going on. The laser, again, will read all the way down to, we spec a 1/2 inch. A lot of cases it'll read much lower than that, and very slow velocity. So if you're going to be dealing with those kind of applications, the laser would be your best option.
All right. Looks like we're wrapping up our questions here. We got one more on how would an internet disruption affect the data since the software is cloud-based? So we're talking about the Flowlink Cipher software. So as far as, the data is going to push on regular intervals. You could have it push, once a day, every 12 hours, 4 hours. If it misses a push for some reason, it will capture the data on the next time it pushes the data. So as far as the field instruments, they're going to log the data. So we got some redundancy built into it. So the instrument out in the field will store the data as well on the cloud. And it'll automatically push the missing data. If for some reason it doesn't get it, we do have the ability to call up the site and download the data and then put it into the Flowlink Cipher. Or if somebody's out on site and say the antenna was damaged due to vandalism, you could go out there, extract the data from the instrument, and then you could easily just push the data into the Cipher software.
Okay, I got one that just popped up. I have submerged flume conditions. What do you recommend? Okay, and this is one that we do get quite a bit. And a lot of times people have put flumes in, installed those years ago. They were rated for what they had for flow, and the community's grown or decreased depending on where you're at. And but a lot of times when these flumes surcharge, then we're getting obviously bad readings. So what can we do, or is there something we can do? With the signature flow meter, Darrell showed you that, we're able to connect up to 9 different technologies at the same time. So what we have done in the past, we put an ultrasonic sensor over the flume. We'll put a laser upstream, and we will actually use both of them to calculate flow. But once the flume goes underwater or surcharges, then it will automatically switch over to the laser and give you one flow rate based on laser. So seeing a lot of this, again, it's nice that we have the ISCO handbook to pull out and look at the level and make sure it did the math right. That doesn't necessarily mean the flow meter or not the flow meter, but doesn't mean that the flume is working right in that application. So a lot more applications where we are using this, dual purpose kind of design. So anyway, great question. With that, that's all I have, Darrell. I'll let you wrap up.
All right. Hey, Rick, thanks for bringing the Flow Data Handbook to my attention. I wanted to mention that we do have a app. We've got an app for that. So if you go to for your iPhone, go to the Apple Store and look for ISCO Flow Calc. And then it has the Flow Data Handbook, the 86 different flow conversions built into it. Plus it has the area velocity flow conversion. So I highly recommend you go to your local app store and download the ISCO Flow Calc app. That way you always have that data tables with you.